Hi guys, today we will talk about the switching losses, how to estimate the switching losses of a boost converter. Now you know that the boost converter, it is done like this, with an inductor L, transistor Q1, another transistor Q2, and the output capacitor C. Now basically you can add also a diode here, which is used as a dead time conductor. So let me give this. The red is T-on. During the T-on period, Q1 is closed, and the inductor charges the current flows like this. And during the period of T-off, you will have this path instead. And during the dead time, since none of these two are active, you will still have the diode conductive here. And to estimate the switching losses, you first need all the parameters that you actually need for the current, and so the waveform are like this. And you need the inductor peak current, the RMS of the inductor, and also the minimum current of the inductor. To estimate the switching losses of these two switches here, it is important because if you then plug the losses into a thermal model, which is made more or less like this. This is the temperature ambient, and these are the junction resistor, junction case, junction ambient. This is junction ambient. This is junction case, and there is also junction heatsink. Blah 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 blah. You will have the maximum temperature reached here. So basically, it is like plugging the power losses here. The thermal resistor are measured in Celsius over watt. So just a few calculations, Celsius over watt times watt, you have Celsius. So you can estimate how much heat you have to dissipate. So let's take the EPC2204, which is not so good because it has the 6 million, but I found this on LTSpice, so we will have to be arranged like this. I will first simulate the boost converter a little bit, so give me some second. It is the most basic boost converter that you can see. Okay, so I will not make any driver, anything, just a boost converter with 2.2 micro and a voltage generator here with a gate resistor, and really that's it. So a very simple boost converter. Let's put just 1 ohm, and let's put the classical dot param d equal to, I don't know, 0.4. We will see later. Dot param fs equal to 400 kilohertz. So this is just the most basic version of the boost converter, without any complication at all. Very simple. And as I said before, we will add this diode here. A Schottky diode to reduce the drop. It should be enough. And an output capacitor of 100 micro with, I don't care about DSR, so let's put a milli just to reduce the ripple, but to reduce the ripple, sorry, to reduce the rerush. And let's put just 1 ohm as ohmic load, the same gate resistor for both of us. And let's just put the classical pulse between 0 and 5 volts, rise time of 10 nano, fall time of 10 nano, and d over fs here, and 1 minus fs. Let's subtract the dead time. Let's copy this, paste it here, and let's translate this guy to a period of d over fs, and let's use the complementary switching period 1 minus d. So let me move this already, let me put just 1 ohm. And if I run the simulation with 10 milliseconds, we should, oh sorry, let's put 20 volts just for as an example. We should see, sorry, I forgot the time.param dd 20 nanosecond. Let's hope that it is enough to prevent shorts, and now it should work. So, okay, it is still in the transient, but after 1 millisecond it should be done, and indeed it has. So let's check that if I said before it is true. This diode here should be conducting in the dead time, and as you can see, it is actually true. It is conducting in the dead time. This will prevent this guy here to reduce the losses of the high side, and these losses here we will be calling reverse conduction losses. Now, to estimate the losses in LTSpice, you have just to press Alt in this, and just zoom on a steady state interval, and just press Ctrl Alt on this. So he says that the average dissipation is 7.74 watts. And for the high side, let me do the same. Delete the diode. Come on. Come on. We have 8.102 watts. This is because we are in high load condition, and as you can see here, it's not that high of a switching loss condition. It is more conduction losses. If you zoom, you see that there are more conduction losses than ever. And so it is because we are in high load, and the high side and the conduction losses are prevailing over the switching losses. But if I put a light load, you will see that the high side has not so much losses. Because it is not switching. This guy is not switching, so it has a negligible loss, a negligible switching loss. Now, if we zoom here, you will discover just that outer range for this guy, and you see that it has just 34 milliwatts, and this guy above instead it has. Let me put an higher load, 10 ohms. Okay, so let me put this. Okay, so the low side has half watt, and the high side has 94 milliwatts. So as it should, because the high side should dissipate less at a certain interval range. Now, if you put the diode here, it has the reverse conduction losses, and there are very, very few. So with this trick, we can even estimate the efficiency with LTSpice. But now we want a method, also another method to estimate these losses on a real script. So for this reason, I created a script in which I will show you how to create a script for the switching losses. First of all, I suggest that you use the international system prefix like this, because it will be very, very useful onwards. Then you have to import this, which is basically all the parameters that you need for the EPC2204, and that's basically gate charge, gate charge, switching charge, the plateau voltage. So every device parameter that you need, which you can find on the datasheet. Most of them you can find on the datasheet. Other you have to calculate with some formulas which you can find in application note. In particular, this Q switch, it is defined in this application note here, END9083. It is the Q switch. It is basically the charge which is required to switch, and it is a very interesting definition. It is basically, you can define it in two ways. This is the first, 1/2 QGS plus QGD, and the other way, which this guy uses, is to where it is written. I already forgot. Should be written around here. Okay, it is using the QGS after VGS plus QGD, which is more or less similar to this. Okay. Because he says that the switching charge required, it is the switching, now you know that the gate charge, it is done like this, okay? And at this point here, you have the VTH, the threshold voltage. So he says that the switching charge, it is from the QGS, so after this point onwards, plus to the voltage of the driver that you need, 5 volts, for instance. And so all of this is the QGS for him. I tried this method and it is quite reliable, I think. And as you see, it take the Q switch until 4 volts, 4.5 volts. It is quite reliable, and I will use this. Okay, I will use this method here. So as you can see, it is very useful to consult application note, because it is the best way to have reliable results. So it is used the Q switch here, and the T switch, it is calculated by basically a simple theorem. You know that it relates the charge, resistor, current, and time. And basically, you know that the current here, it is given by I times delta t, because the current, for definition, it is Q over delta t, is the charge flowing in the time, coulomb for seconds. Now, if you relate also with the equation of the capacitance, the capacitance, which is C equal to Q equal to C dV, if I remember the basics of physics, should be like that. You can relate, you can somehow recover this equation here: charge over voltage over resistor. And it is basically the turn on and the turn off switching, which you can calculate here. And most of the losses are in the switch, in the circuit, because if you see that the inductor losses, they are ridiculous, very ridiculous. It is true that I didn't put the series resistance, which will be 2 milli, for instance, because I wanted to be very, very beautiful. So, but let's calculate this. Okay, so now half here and half here, and we will insert step by step everything that we need. I suggest you to skip this part. So let's find it. This is the gate voltage. We will put the typical, which is 1.1. Then we can also use the variation of the VTH in time, if you really want to do that. You have just to you can calculate this, the VGS source gate to source voltage characteristic, and you can calculate how the threshold voltage varies with time. Honestly, you can do that. And you can have a more reliable result. But in this, for this time, I will skip it. By the way, the equation is this: VTH equal to VTH times 1. But it is not so important. So let's just use this as VTH, and that's it. The RDS, the drain source resistor, can be found here in the first pages. Should be found here. Okay, it is 4.4, and now we should see the variation of the normalized resistor towards the maximum temperature, and it is more or less 1.72. if you see, around 125 milligdegrees. And we will put the RDS hot, so 4.m, and the RDS hot is RDS times 1.72. And we will have the maximum value, which is more or less, this is a repetition, by the way. Now, let's use the COSS. COSS is the output capacitance, and we have 465 pico. CESS, which is the input capacitance, which is 850 51. Now we have the charges. Total gate charge, it is 7.4. QGD, it is the 0.8. QGS, it is 1.8 nano. And we can even use the definition of QGS1 and QGS2, which are in other application note. I saw this in other application note, but now we don't need the definition of QGS1 and QGS2. This is the Vishay application note if you're interested, but now we don't care. So we need also the plateau voltage, which is here around 2 volts. This is also important for the switching losses. DRG of this EPC should be around 0.5, gate resistor 0.4, and indeed it is. The GFS, it is used for the variation. The forward transconductance can be even used, but I never saw the. It is this ratio here, and the EDS over VDS. You can use it. You can use this guy in also to make the variation of the drain source voltage over the VDS, but it is not so important. You will see that even just with a simple code like this, you will arrive to have more or less the same result as LTSpice, or even in a worst case way. Now the V driver is the VGS voltage, so the driver voltage that we're given, so it is here the 5 volts. You see that the higher the voltage and the less the radius on. It is very not recommended to use this voltage here, because as you can see, the radius on resistance will increase as well. So now you are in the 5 volts, and you are in the best range of this resistor. Now the internal resistor of the driver we don't know, so we put just 0, and the gate resistor external, it is 1. So the total resistor of the on, which the signal we see, is the internal resistor plus the external resistor plus the G of the EPC. And the same for the off. We don't have the this is a very simple circuit, so you don't have the turn on turn off path. Just the turn on, the turn off will take the same path, so it is always 1. Sorry, my mistake, it is also 1. And now, as you can see, I've already prepared the print of the conduction losses, the VDS, the VC, V in, V out, the first switch, everything. I prepared everything. Okay. So now we need the parameters of the inductor. So we need to know how many. So we need to calculate first the parameter of the inductor. So if one and end, we need to know everything about the inductor. So we need to know this equation here. You can find in main application note or even in literature, but basically the EL max, it is given by the input current, because you always have to remember the circuit here. It is given by the input current I in plus the ripple delta EL over 2. This is the ripple, okay, and this is basically the offset current, and the ripple it is given delta L. It is given by V in over L times D over F switch. So these are just equations which you can find on the web. I will just report it on here. So let me use V in equal to 20. Then V out equal to 40. The duty cycle, the power output which I want is 1 kilowatt. So 1 times K. Okay, let me put like this, because it is better. The dead time is TD equal to 20 times nano. So 20 nano of the dead time. We will use the as a load We will estimate the efficiency, for instance, to be 0.95%. So I will expect this to be very efficient. The input voltage is given by the output voltage times the output voltage over the input voltage over the efficiency. The output voltage we will set, I don't know, we will set the load. We don't even need P out, actually. We need to define the out before, otherwise you won't be able to read it. Let's set a very simple output current, like 10. Okay, we'll set 10 as an output current. So the resistor to insert in LTSpice will be V out over I out, which is 4. This resistor will be 4. And now let's put the inductor L equal to 2.2 micro times micro, and the switching frequency F switch it is very high, so let's put 50 kilohertz, 50 times K. Let's modify it on LTSpice as well, so that the choice of the inductor is more consistent for this kind of load. And the forward of the diode, I don't really know. What is the forward of this diode here? Let me check. No, you can't check in this way, sorry. You can't. I should be able to do like something like this, and this should be the difference between this voltage here, 32. Let's say 2 volts. Let's say that in high load condition, 2 volts. The duty cycle of the boost is the output voltage minus the input voltage over the output voltage. You should know the ripple of the inductor is, as I said before, V in over L times D over F switch. And the maximum current, IL max, it is equal to E in plus DL over 2, and the minimum inductor current, L min, it is equal to E in minus DL over 2. You can use you can use the RMS. You can use the RMS of the switch. Since these will be used to calculate the conduction losses, the switches have a waveform like this, and you can't use neither the minimum neither the maximum. You have to use the RMS, which is more or less like this. It is not the input current, okay? It is not correct to say that the RMS here, it is the input current, because you have an interval here which is not doing anything. So the RMS, it is given by a very not so beautiful formula. It is given by D over 3 times something. I will write it directly on here, but you need this. E switch ESV RMS, it is equal to D over 3 times IL min to the square plus IL min plus IL max plus IL max to the square. This is a square root, so you have to elevate to the 0.5. The same it is for the other switch. Okay, just take the other interval. So you switch RMS, this is the low, and the other is H. So instead of D, you have to take 1 minus D. Yes, because the duty cycle D, commands the main switch, which is this. Remember that in the original boost converter, you use just a diode here, okay? So D operates this. So this is for the low, and this is for the high, 1 minus D. And the bus voltage, so V bus, which is blocking, so the maximum blocking voltage of this guy here, it is not just the out as it should be, the output voltage as it should, because let me check this. You see, it is the output voltage, but you have also to consider the forward of the diode here, which is consistent. So we can't neglect this. V bus is equal to V out times V forward. And with this, we inserted all the parameters of our converter. So the beautiful things of the script is that you can just insert this, and you will have automatically all the losses calculated. I think that it is very beautiful. So now we have to calculate the losses. So again, if one, I do this just because if I wanted to cover like this, I can do that. Cover this because I don't need it, and cover this because we already inserted them, and also cover this. Cover this, and let's use the this is the converter parameters. And now this guy is instead the conduction losses, switching losses in general. And first, let's calculate the conduction losses. The conduction losses are given by the resistor. So PC over LS, it is equal to RDS hot times E switch RMS square. So this is nothing new under the sun. PC HS, the same, but the other one, H. Now, so these are the switching and conduction losses. So these are the conduction losses. Now, reverse recovery losses. These are basically the dead time loss. These are the reverse recovery losses for both of them. PRR of LS are equal to 0 because the gun has no body diode theoretically, and so we will put them to 0. Then we have the COSS losses. The COSS are the output capacitance losses, and the I side has 0. PCOSS I side is equal to 0 because it doesn't switch. It has 0 voltage properties. Okay, now I will see. I will get probably I will get killed by the physicist, but or I will get killed by the mathematicians. But really, let's discuss this on the comment. I think that you shouldn't consider so much the switching losses of the I side. I think. Then if you propose some method, but I think that they are negligible in comparison with the conduction losses. You didn't calculate the I side losses. You are a very bad YouTuber. You can if you want, but honestly, you will see that it is not very relevant. So the conduction losses instead for the low side, PCOSS low side, it is given by an integral, the integral of 0t VDS COS. You take COS outside, so you have the integral of 0t VDS in dV. How you should calculate this is 1/2 COS VDS square, basically. And let's insert this. So 1/2, oops, I forgot the switching frequency, times COSS times VBus square, because it is given by the integral. Then we have the gate losses. The gate losses are given by the resistor, basically. So PG, it is equal to PG I side, it is equal to F switch times QG times V driver that we are using to drive the MOSFET. And the low side here, it is the same, basically the same. Now, we have the reverse conduction losses. Conduction. The reverse conduction losses are given mainly by the high side diode here, because it is conducting when effectively none of them are conducting. So we have to calculate only for the high side. So PTD low side equal to 0 because the low side is not conducted. In the high side, PTD H of S, it is equal to the dead time TD times the switching frequency times IL min times IL times V forward. This is for the on period, because in the low side you do this, and in the high side you do that. Oh no, sorry, it is the opposite. So in the high side you use this. But I don't really care. I don't care. I just wrote something. I just write. So this is for the off, and this is for the on. But honestly, I don't care. I don't care because at the end of the day, the PTD H of S, it is the sum of these two. So I really don't care if it is in the on or the off, because we will see that it is the sum of these two. And now, finally, switching losses on low side. Finally, the switching losses on low side. Let me save up to this point, save file. We finally have the switching losses to calculate. Okay. We can have different methods to calculate this. And I will use, as I said before, I will use the END method. So I will use this formula here. Before doing that, we need to calculate the turn on and turn off times. And so, let's do this. I have to insert also the print for the guy. But switching losses. So the switching losses for the high side, as I said before, P switch high side is equal to 0. Let's discuss this. Okay. And we have to calculate the T on, which is the Q switch over the. Now let's check again. Can I reload? Reload. Okay. The on period, it is given by VGRD minus VGP, or what are these animals? VGDR, it is basically the voltage which you use to turn on this guy. And so in our case, we will have V driver. Yes, we will have V driver minus V plateau over RG on. I think that I missed some bracket here. T off, it is equal to Q switch, but now we don't have to arrive to we don't have to use again the driver voltage, because you're not turning on. So you have just the V plateau over RG off. Now I remember why this equation is like this, because V over R is I and Q over I is T. Simple as that. So you have T, which is equal to Q over I, but I it is equal to V over R. V over R. Just like that. It is simple like that. Okay. And now that we can have T on and T off, we can calculate the switching losses P switch low side. The P switch, the switching losses of the low side which is where did I wrote I didn't write total losses EPC gun lead of LS loss. Ah, okay, because then I make the sum of everything. And but I don't like this, so let me use another print. Switching loss. P-switch low side. Okay, now it should be good. I don't need this. In another script of mine, I calculated the 4 times the switching losses with different results. I used the Vishay, I used the gun lead of, I used everything, because you can also take the gun lead of. It is a book which you can find, Alex gun lead of. I have installed this. But anyway, you can find the gun lead of, and he will propose another method to calculate the switching losses. So now, let's use this formula here. So VDD times ID times these two guys here. So let's insert this. 1/2 times F switch times VBus times the IL max times T on plus IL min plus T off. Because the reason of this formula, it is basically that you have the VDS, which is doing like this, and the current, which is doing like this. So when you are, so you take the minimum here in the turning on, and you take the maximum in the turning off. This is T on, because this is the VDS, and as you can see, it is 0 here, and it is the off period. And so the formula should be like this. Sorry, maybe it is the opposite. IL max times T on. Let me check for a minute. Let me check. Maybe I did some exactly the opposite. Maybe I was wrong. When you are turning on, it is the minimum. So yes, I did say it right. I did say it right. Ah, yes, but since the turn on and turn off will be probably equal. But this is IL min. Let's put things correctly. Okay. Now, if you run the script, you see that let me use preferences. Let me run the script.